first, let's recall what we have learned so far in the chapter of subgroup. What is a subgroup? Suppose G, O is a group and H is a non-empty subset of G. Then if H, O is itself a group, then we will say that this H is a subgroup of G. So that was the definition of subgroup. Now there was two conditions of finding a subgroup. What are the conditions? Number one condition was that A, B belongs to H. This will imply A composition B belongs to H, A inverse belongs to H. If this happens, then we can say that H is a subgroup of the given group G. And number two was that A, B belongs to H. This will imply AO B inverse belongs to H. If this happens, then we can also say that H is a subgroup of the given group G. Now this was the two specific condition for finding a subgroup of a group. Now here we have another theorem, and this is particularly applicable for finite subgroup. That is a subgroup or a subset which contains a finite number of elements. Then we can apply this theorem here. The theorem states that let G, O be a group, and H be a non-empty finite subset of G. H be a non-empty finite subset of G. Then H will be a subgroup of G if and only if. Then H will be a subgroup of G if and only if A, B belongs to H. A, B belongs to H. This will imply A composition B belongs to H. If this condition satisfied for any finite subset of a group, then we can say that this subset will form a subgroup of this group. Let's prove it. It's an if and only if condition. At first we will prove the if part or the necessary part. What will be the necessary part? That is, let H be a subgroup of G. Then we have to prove this condition. Now if H is a subgroup of G, it will obviously satisfy the closure property because it is itself a group. That means whenever A, B belongs to H, this will obviously imply A composition B will also belongs to H. So the if part is proved. Next, the sufficient part. Conversely, let this condition holds. That is, whenever we find A, B belongs to H, this will imply A or B belongs to H. Now we have to prove H is a subgroup of G. That means H is itself a group. For being a group, we have to prove total 4 properties: closure, associative, identity, inverse. Now check this condition. For this condition, we can say that closure property is already satisfied. That means whenever we are taking 2 elements, their composition belongs to this set. So closure property is satisfied. Next, associative property is an hereditary property. As we know, hereditary property is a property which satisfies for all the subgroups. So if G is a group, this is associative, then H is a subset, will also be associative. Now we have to prove the another 2, which are identity and inverse. For proving this, let us consider some H belongs to H. Okay, and we are considering H, H square, H cube, and so on. Now H means this is H, H square is H composition H, H cube is H composition H, composition H. This all belongs to our set H because we have this property: whenever we take 2 elements, their compositions belongs to H. That means all H, H square, H cube, H to the power 4 and so on will belongs to H. Now it is given that H is a finite set, right? And we are considering an infinite collection. Then all of these elements cannot be distinct, right? If it all are distinct, that means they are all infinite number of elements belongs to H, which is a finite set. This is not possible. That means there will be some of the element which will be equal to other members. Let us suppose some H to the power R equals H to the power S. Suppose this is 0, this is S, this is R. h to the power s equals h to the power r, where let us take r greater than s. Okay, that means this will imply h to the power r minus s, this is equals e, right? Now r minus s is again a positive integer, that means we are composing h, composition h, all of this r minus s times. That means this quantity will also belongs to h, that is h to the power r minus s, this belongs to h. Now this is equals e, that means our e also belongs to h, which is the identity element. So the identity property is satisfied for being a group. Now we have to prove the inverse property. Now we have taken that r minus s, r greater than s, right? That means r minus s, this will obviously greater or equal to 1, because they are all positive integers. Their difference, if they are equal, their difference will be 0, and if not, it can be 1, it can be 2, 3 and so on. So r minus s will always greater or equal to 1. That means r minus s minus 1, this is greater or equal to 0. Now consider h to the power r minus s minus 1. This will be an element of h because this is a positive integer, non-negative integer, right? Now we are taking the composition h to the power r minus s minus 1, composition h. What will be its value? This will be h to the power r minus s. This is again equals to e. This is equals e. Now take these two elements, this and this. We are composing this element with h and we are getting the identity element. That means this element is our h inverse, right? So we have taken any arbitrary element h in our set and we find its inverse. That means inverse exists for all the arbitrary elements. So inverse property is also satisfied. That means H itself a group, that is H is a subgroup of G. This proves the theorem. Next theorem is about the intersection of two subgroups. That means the theorem states that let H, K be two subgroup of G, then H intersection K will also be a subgroup of G. The proof is very easy. Let's take two subgroups. Let H, K be two subgroups of G. Okay, we have to prove H intersection K is also a subgroup. Now let's take A, B belongs to H intersection K. That means A, B both are belongs to H and belongs to K also, as they are belonging to the intersection. Now H is a subgroup. H is a subgroup. So A, B belongs to H. This will imply A composition B inverse belongs to H. Similarly, K is also a subgroup. So A, B belongs to K. This will also imply A composition B inverse belongs to K. Now take this line and this line. From these two, we can conclude that A composition B inverse belongs to H intersection K. So we are taking any two elements belongs to H intersection K and we find that A composition B inverse is also belongs to H intersection K. So from here we can conclude this is also a subgroup of G. Now we cannot conclude the same thing for H union K. That means whenever H and K are two subgroups, we cannot conclude that H union K is also a subgroup. No, because let's take a counter example. Let H equals 2Z and K equals 3Z and our group G is equals Z, obviously taking with addition Z plus. Now 2Z, that means the multiple of 2, all the elements will be multiple of 2, and 3Z, all the elements will be multiple of 3. This H plus and K plus both are subgroups of G, we have to check that H union K is a subgroup or not. Now sum 2. This belongs to H union K because 2 belongs to H, and let us take 3. 3 also belongs to H union K because 3 belongs to K, right? Now composition of 2 and 3. Here the composition is addition, that is this will be equals to 5. Now find does not belongs to H and does not belongs to K, because 5 is not a multiple of 2 and not a multiple of 3 also. That means it does not belongs to H and does not belongs to K. That is 5 doesn't belongs to H union K. So it doesn't satisfy the condition for being a subgroup. So H union K is not a subgroup of G.